આપણી પાસે છે ડૉક્ટર શૈલેષ શિરાલી, એ સહ્યાદ્રી સ્કૂલના ડાયરેક્ટર છે. એમણે ફિઝિક્સમાં બેચલર્સ કર્યું છે દિલ્હી યુનિવર્સિટીથી. એમણે આપણી IIM અમદાવાદથી MBA કર્યું છે. એના પછી યુનિવર્સિટી ઓફ ટેક્સાસથી PhD કર્યું છે. એ જે કૃષ્ણમૂર્તિથી ઘણા ઇન્સ્પાયર છે અને એમની સ્કૂલ્સના પાર્ટ રહ્યા છે 1983થી. He also have a great interest in Python, Heel and cultural hurt. So we have Shailesh Shirali.
Thank you very much. Namaste. Namaste to all of you. I'd like to thank IIT Gandhinagar for this kind invitation to meet all of you. And I'm sorry that it is online and I can't be in front of you in person, but unfortunately that did not work out. So I'm going to be talking about this particular topic called combinatorial thinking, which is not emphasized much at the school level, but it is something which can be exposed to, can be talked about at the school level very easily. And there is some interesting side of ancient Indian mathematics also which comes here. So that is also of interest. So let me start without any further. So I'm going to be sharing some very beautiful examples of combinatorial thinking with you. And what does the term mean? It means that we are interested in counting, but we are not going to do it by the complicated brute force. We are going to try to use the structure of the problem to get the answer. And often mathematicians consider that combinatorial proofs are very elegant. They look very beautiful because you get the answer without too much calculation, without too much algebra. And so they are considered to be more elegant than algebraic proofs. And they illustrate the power and beauty of simple ideas. So we're going to study a few of these examples today. And I have written at the end, I feel that such proofs need to be known better at the high school level because they are simple and understandable. So let me show you a few examples, very simple examples, and then we'll go into the main part of the lecture today. So let's prove something, a simple identity. So can we put this into a combinatorial form? Well, here, suppose you consider this set here, all the numbers from 1 up to n+1. There are n+1 elements in the set. So how many pairs can you make? How many possible pairs are there in which both the elements belong to this set? The elements can be the same. They can be repeated. Well, there are obviously n+1 squared pairs, right? Each I can take n+1 possibilities, so can j. Now we subdivide the pairs according to how...
Professor Shailesh, maybe we want to translate the first part.
Yeah, please. Take care. Yeah.
સર કહે છે કે જે આપણે કોમ્બિનેટ્રિક્સ વાપરીએ છીએ, પરમ્યુટેશન છે, કોમ્બિનેશન છે, તેનો એલ્જિબ્રાની સાથેનો શું ટચ છે એની વાત અત્યારે થશે. જેમ કે n+1 હોલ સ્ક્વેર છે તો આપણે ખબર છે a + b હોલ સ્ક્વેર a² + 2ab + b² જેવી રીતે હોય છે. તો એનું કોમ્બિનેટ્રિક્સનો યુઝ કરીને આ ઇક્વાલિટી કઈ રીતે આવે છે એનું હવે આવશે. જેમ કે સર અત્યારે માનું છે i અને j છે એ નેચરલ નંબર્સ છે ફ્રોમ 1 to up to n+1 છે. તો i j ની આપણે કેટલી અલગ અલગ પેર્સ બનાવી શકીએ. જેમ કે ડાઈસ છે તો 1 થી 6 હોય તો એવી કેટલી તો 36 થાય. તો આ છે તો n+1 પેર્સ થશે.
Yeah. Okay, so now all these n+1 pairs, n+1 squared pairs, I'm going to subdivide them into 3 categories. The categories are according to how many ones they have. Obviously, since there are 2 numbers in the or there's just one or no one at all. If there are no ones, then that means you're choosing both the numbers from 2 up to n+1. Right? That means the 1 has been left out. So there are only n possibilities for that number I. So there are n squared such pairs where there are no zero ones. Now, how many are there in which there is exactly one? If there's only one, that means one of the number in the pair is already chosen. So you have to only choose the other number in the pair. It should be something not 1. It should be one of the numbers from 2 up to n plus 1. So there are n possibilities. And it can be switched. Either it is 1 comma that number or that number comma 1. So there are 2n possibilities. And of course, there is just one pair in which both the numbers are 1. 1 comma 1 itself. So yeah, n squared pairs with no ones, 2n pairs with exactly 1 1, and 1 pair with 2 ones. So n plus 1 whole squared must be equal to this plus this plus this. So the identity follows. I hope that is clear. So yeah, go on please. Yes.
तो अभी हिंदी में आपको समझने को मिलेगा ये। तो n इन्होंने बोला कि कैसे हम n प्लस 1 जो आई जे पेयर है उसको हम कैसे लिख सकते हैं। तो उसमें आप पहले देखिए आई और जे में से हमने सोचा कि 1 कहाँ आता है, ठीक है, 1 आएगा कि नहीं आएगा, सारे पेयर में तो 1 नहीं आएगा, है ना। तो अगर जिनमें एक भी 1 नहीं, आई भी 1 नहीं है, जे भी 1 नहीं है, ऐसे कितने पेयर होंगे, n स्क्वायर, है ना। और फिर एक आई, अगर एक आई या जे में से कोई भी एक अगर 1 हो तो चलो मानो आई 1 ले लेते हैं, ठीक है, तो कितने आएंगे, n मिलेंगे आपको, है ना, 2n क्योंकि पलट के भी, है ना, पलट के भी।
Okay, so shall I move on?
और फिर लास्ट में एक बचेगा। तो ये n स्क्वायर क्या चीज है, n स्क्वायर वो सारे पेयर्स है जिनमें 1 1 नहीं है और बाकी में एक 1 है और लास्ट वाले में कोई 1 नहीं है, 2 1 है एक्स्ट्रा, है ना।
Right. So I'll move. Yeah, so that therefore it follows. So this has been now subdivided into 3 categories, and therefore n plus 1 whole squared will be equal to this quantity plus this quantity plus this quantity. So I look at another such identity. Now I am using this symbol. Sometimes in the school books, they use C. They'll write m plus n C2. Well, this is the same thing. So what I'm going to prove is m plus n C2 is equal to mc2 plus nc2 plus m times n. So I'm going to prove it without trying to expand this algebraically. You see, you can always use algebra to get the same thing because we know that nc2 is equal to n times n minus 1 upon 2. We can substitute everything and see if it is true, but I'm not going to try like that. So take a set which has m plus n elements. There are, how many ways can you select 2 elements from this set? Well, it is m plus n choose 2, m plus n C2. Now partition this set, break it up into 2 pieces, call them A and B, in which A has m elements here and B has n elements. So you've got, now look at the possible ways of selecting 2 elements. Either both the elements are from A, or both the elements are from B, or there is 1 element from A and 1 element from B. That covers all the possibilities, right? So you have subdivided S into 2 parts, A and B. So if you have to select two elements from the whole set, either both of them are from A, or both of them from B, or 1 from A and 1 from B. Both from A means there are M choose 2 possibilities, MC2. If both from B, then there are NC2 possibilities. And if 1 is from A and 1 is from B, there is M multiplied by N possibilities. So that means M plus NC2 is equal to MC2 plus NC2 plus MN. Okay? Does that make sense? I hope.
Okay. આપણે m પ્લસ nc2 હોય તો એનું ફોર્મ્યુલા આપણે હંમેશા સ્કૂલમાં રટાવી દઈએ કે m પ્લસ nc2 છે mc2 પ્લસ nc2 પ્લસ mn. બટ આના માટે આપણે બીજું એક લોજિક પણ સરે કીધું કે આને ડાયરેક્ટલી કેલ્ક્યુલેટ કરીને ન કરીએ વેરીફાઈ, બટ આને આપણે એક મેથડ સર આપી. આપણે એક એવો સેટ લઈએ છીએ s જેની કાર્ડિનેટી એટલે નંબર ઓફ એલિમેન્ટ્સ ઇન s છે m પ્લસ n. હવે એ સેટ આખો છે એમાંથી આપણે બે વસ્તુને ચૂઝ કરવાની છે. તો એ આપને ખબર છે એનું ફોર્મ્યુલા m પ્લસ nc2 વિચ ઇઝ LHS ઓફ ધીસ ઇક્વેશન. હવે આ જે સેટ s છે એને આપણે એવા 2 પાર્ટમાં પાર્ટીશન કરવાનું છે જેનું નામ આપ્યું છે એક સેટ A એક સેટ B. સેટ A ની કાર્ડિનેટી એટલે કે A માં m એલિમેન્ટ્સ છે, B માં n એલિમેન્ટ્સ છે. એવી રીતે આખા સેટને બે પાર્ટમાં ડિવાઈડ કરવાનું છે. તો m+nc2 છે એ શું છે? એ છે કે આપણે જે ઉપર m+nc2 બે એલિમેન્ટને ચૂઝ કરવાના છે એ કેની પ્રોબેબિલિટી છે? જે બે પાર્ટમાં આપણે ડિવાઈડ કરેલ છે A અને B, એમાંથી બે એલિમેન્ટ આપણે સિલેક્ટ કરવાના છે. તો એ બે પાર્ટીશનમાંથી કાં તો એક A માંથી બે એલિમેન્ટ છે, કાં તો B માંથી બે એલિમેન્ટ છે, કાં તો એક એલિમેન્ટ A માંથી છે, એક એલિમેન્ટ B માંથી છે. તો એની જે પ્રોબેબિલિટી છે એ કા આમાં છે, કા આમાં છે, કા આમાં છે, તો ઓર આવે છે, એટલે એડિશન થશે. એટલે એ જે પ્રોબેબિલિટી છે RHS થશે અને LHS છે m+nc2.
Oops, sorry.
બીજી રીતે સમજાવું ખાલી.
હા સર.
ठीक है.
સપોઝ આપણો જ આ ક્લાસ છે, m+n છે, m પુરુષ છે અને n સ્ત્રી છે. હવે m+n માંથી બે વ્યક્તિને આપણે કમિટી બનાવવાની છે. તો એ જે કમિટી એટલે ટોટલ પ્રકાર કેટલા થાય સિલેક્શનના? તો કે ટોટલ m+n માંથી બે. હવે એમાં કન્ડિશન મૂકી દઈ, ના એક સ્ત્રી ને એક પુરુષ હોવો જોઈએ. તો બે માંથી એક એટલે mn લખ્યું છે, mc1 nc1. બંને પુરુષ હોવા જોઈએ કે બંને સ્ત્રી? ટૂંકમાં ત્રણ રીતે આપણે પાર્ટીશન કરી નાખીએ, આપણે કટકા કરી નાખીએ તો આપણે આ રીતે કરી શકીએ. કાં તો બે પુરુષ હોવા જોઈએ, કાં તો બે સ્ત્રી હોવી જોઈએ, કાં તો એક પુરુષ ને એક સ્ત્રી હોવું જોઈએ. બંને પુરુષ હોય તો mc2, બંને સ્ત્રી હોય તો nc2, અને કાં તો એક પુરુષ એક સ્ત્રી, ત્રણ પ્રકાર થાય. એટલે એક જ જથ્થામાંથી આપણે બે સિલેક્શન કર્યા, એક ટોટલ માંથી કર્યા અને કટકા કરીને કર્યા, તો એ બંને પ્રકાર કેવા હોય છે? સરખા થાય. એટલા માટે ઇક્વાલિટી સરખી જ રહેશે હંમેશા.
Great. Thank you. Okay. Now, this one, maybe we don't have to spend so much time on it. It's the same idea. So this is well-known identity. Sum of the first n odd numbers is equal to n squared. So it's the same idea as the first one. We won't spend. So if you consider all possible pairs from this set, there are n squared such pairs. Now we subdivide the pairs according to the maximum value in the pair. Since all the numbers are from 1 to n, the maximum value can be either 1 or 2 or 3 up to n. If you say the maximum value is 1, that means both the numbers are 1. So there is just one such pair, right? If maximum value out of I and j is 1, that means both I and j are equal to 1. And there's only one such pair. If you say the maximum value is 2, then there are possibilities are 1, 2, 2, 1, or 2, 2. There are three pairs which have maximum value 2. Similarly, if you say the maximum value out of them is 3, then the possible pairs are 1, 3, 2, 3, 3, 3, then 3, 1, and 3, 2. So there are 5 such pairs. And you can see it just goes 1, 3, 5, and so on. So it's similar to the first problem, first example. So maybe it may not be necessary to fully explain this again. Do you think it needs to be, we need to go into it?
આગળનો જે ફર્સ્ટ પ્રોબ્લેમ જો એના જેવું જ છે, સમજાવવાની જરૂર છે કે સમજાઈ ગયું બધાને? સર યુ કેન કેરી ફોરવર્ડ.
Okay, so I'll go on. Please now some simple ones. So here is a very simple one, very well known. The sum of all the binomial coefficients of up nc0 plus nc1 plus nc2 up to ncn is equal to 2 to the power of n. And I'll just give a one-line proof for this. All that we have to do is count all the subsets of an n element set in two different ways. Either we say we count them according to how many elements there are in the subset. So how many subsets are there with 0 elements? NC0. How many are there with 1 element? NC1. These many with 2 elements. These many with 3 elements, and so on. These many with n elements. So if you add them all up, that means you're counting all the subsets with all possible cardinalities. And it's easy to see that that number has to be 2 to the power of n, because each element in the set is either selected or not selected. It has there are 2 choices for each element. 2 choices for the first element multiplied by 2 choices for the second element times 2 for the third, and go on all the n. So both sides count the total number of subsets of any set with n elements. So I think this is familiar actually. I just put it in first as an example. It may not need much more explanation. You tell me if I need to stop.
I think they have seen this.
Yeah, this is quite it's a very familiar at the school level. Another familiar one is n choose r is equal to n choose n minus r. And the idea is choosing r elements is the same as choosing n minus r elements and then discarding. That means you throw them away. So choosing r, one way is just to choose r, or you choose the ones which you're going to put away, which you're going to reject. So n choose r is equal to n choose n minus r. This also, I think, is well known to everybody. So this one is slightly more interesting, but again, it is familiar at the school level. N choose r is equal to n minus 1 choose r minus 1 plus n minus 1 choose r. And this is the basic property of the Pascal triangle, that each number in the Pascal triangle is the sum of the two numbers immediately above it. So 1 minute, sorry. Yeah, why does it work? So we have to consider this side, and choose r is simply the number of ways of choosing r elements from an n element set. Now fix any one element of that set. Let's call that element x. Either that x is chosen, that means it is part of the subset, or it is not chosen. If it is chosen, now the problem is to choose r elements altogether. And one has already been chosen. So you have to only choose r minus 1 elements. And you have to choose them out of n minus 1 elements. So this gives you the number of possibilities in which x is already chosen, has been decided to be chosen. And similarly, this gives you the number of possibilities in which you already decided that x is not going to be chosen, that is not chosen, because you have to still choose those r, but now your choice is out of only n minus 1, because x has been put away. So I think this also. So let's go on to the somewhat.
આ ક્લિયર છે બધાને કે એકવાર એક્સપ્લેન કરું? ઓકે, n choose r છે તેનું બીજું બી ફોર્મ્યુલા છે n-1 cr -1 પ્લસ n-1 cr. તો એને બીજી કઈ રીતે જોઈ શકીએ? LHS છે NCR, એટલે કે n આઇટમ્સમાંથી મારે r આઇટમ્સ ચૂઝ કરવાની છે. બીજી બાજુ હવે કોઈ આ n આઇટમ્સમાંથી r આઇટમ્સ મારે ચૂઝ કરવાની છે, તો r માંથી એક એલિમેન્ટ હું ફિક્સ કરી દઉં છું x. તો જે r chosen એલિમેન્ટ્સ છે એમાંથી કાં ઈ x ફિક્સ છે ઈ r માંથી હશે, કાં ઈ r માંથી નહીં હોય. તો એની બે પ્રોબેબિલિટી છે એ અહીંયા આપી છે. અગર જે એક એલિમેન્ટ મેં ફિક્સ કર્યો છે x, ઈ chosen r એલિમેન્ટ્સ માંથી છે, તો હવે બાકી શું બચ્યું? r-1 એલિમેન્ટ્સ માંથી n-1 એલિમેન્ટ્સ બચ્યા છે અને એમાંથી મારે r-1 એલિમેન્ટ્સ ને ચૂઝ કરવા છે. એક ઈ પ્રોબેબિલિટી છે જેમાં x ઓલરેડી આવી ગયો છે r એલિમેન્ટ્સ માંથી. બીજી કઈ પ્રોબેબિલિટી છે કે x ઈ r chosen આઇટમ્સ માંથી નથી. તો હવે મારી પાસે કેટલા બચ્યા? n-1 એલિમેન્ટ્સ, અને એમાંથી મારે સિલેક્ટ તો r જ એલિમેન્ટ્સ કરવાના છે, કારણ કે આપણને ખબર છે કે x એમાં નથી. સો બે પ્રોબેબિલિટી છે. એક ફર્સ્ટ પ્રોબેબિલિટી છે એમાં x ઓલરેડી છે r chosen આઇટમ્સ માંથી. સેકન્ડ જે કેસ આપ્યો છે એમાં x નથી. રાઈટ?
Okay, thank you. Okay, now let's spend a little bit more time on this one, which is another very well-known identity, but let's see. So summation of 1 multiplied by NC1 plus 2 multiplied by NC2, k multiplied by NCk, all the way going from k equal to 1 up to n. And this is equal to n times 2 to the power of n minus 1. So if you had to prove this using algebra, you can do it. It comes from the binomial theorem, or you can use differentiation. I think that's a well-known, but all these are algebraic techniques to do it. So we are going to look at a combinatorial method. So the problem to be considered is this one. From n given persons, how many ways can you select a committee? So the committee obviously has some size. The size is not given. It could be any number from 1 up to n. It's at least 1. or it could be the entire set. How many ways can you select? And the committee must have a chairperson. So, or if you're selecting a team, it must have a captain. So this is the problem. You've got n elements, you have to select a committee, and the size is not fixed. Size has to be also decided, but the committee must have a chairperson. So let's see. So this is the setup. Now there are two ways. Now the standard kind of approach in combinatorial thinking is that you try to count the same thing in two different ways. And from the two different ways, you end up getting some interesting identity. So here we have to prove an identity. So we are going to do this counting in two different ways. So the first way is, so let's fix the committee size first. So obviously, k is any number between 1 and n. So there are k choices. Now select those k members. How many ways can you select the k members? Obviously, there are nck ways. Then, having selected the members, select a chairperson from within those members that you have chosen. Since you've already got those k members, there are k choices for the chairperson. I hope this is clear. So we first decided the committee size, then we select the k members. There are nck ways of getting those members. Then from those selected members, select a chairperson. There are k choices. So if you look at both these, since it is this choice and then you're taking this choice, you have to multiply this k and this nck. So k multiplied by nck, and then take the summation from k equal to 1 to n. So this quantity, therefore, gives you the total number of ways of selecting the committee with a chairperson. I hope that is clear.
Clear?
Now we look at the same problem in a slightly different way. So instead of selecting the members first, let's select the chairperson first. So since the chairperson is selected from the full, you have the full set of people to select from, there are n choices. Now, having selected the chairperson, let's select the remaining members. Now, how many people are there? If you've already selected the chairperson, the leftover set is got n minus 1 people, right? The remaining, all the n, subtract the chairperson. So how many subsets does that set have? Remember that a set with n elements has 2 to the power of n subsets. So in this case, there are n minus 1 elements. So there are 2 to the power of n minus 1 subsets. Any subset can be chosen. And this chairperson can be combined with any subset. So you get n times 2 to the power of n minus 1 ways of selecting the committee with a chairperson. So therefore, since this is one way of counting it, and this is another way of counting it, so these two must be equal. Okay? So does that need more explanation?
સમજાઈ ગયું? કેસ 1 છે, ફર્સ્ટ વે છે એ છે પહેલાં આપણે શું કરીએ છીએ, કમિટી સેટ કરીએ છીએ, કમિટીને ફિક્સ કરીએ છીએ. હવે કમિટીના મેમ્બર્સ ટોટલ આપણે પર્સન આપ્યા છે, n નંબર ઓફ પર્સન છે. હવે કમિટીમાં કેટલા મેમ્બર્સ છે આપણે ખ્યાલ નથી, તો આપણે શું કરશું કે પહેલાં કમિટીનો મેમ્બર ટોટલ કેટલા છે એ ફિક્સ કરશું. એનું નામ આપ્યું છે કે. હવે કેની રેન્જ ક્યાં સુધી હોઈ શકે? 1 થી લઈને n સુધી હોઈ શકે, બરાબર? હવે કમિટીના મેમ્બર ફિક્સ થઈ ગયા કે છે, તો હવે એને એ મેમ્બર્સને ચૂઝ કરવાના કેટલા વે હોય? NC કે એનમાંથી કે મેમ્બર્સને ચૂઝ કરવાના છે, પ્લસ ચેરપર્સન પણ એક હોવો જોઈએ. તો એ જે કે મેમ્બર્સ આપણે સિલેક્ટ કર્યા છીએ એના કેટલા વેઝ હોઈ શકે ચૂઝ કરવા માટે? ચેરપર્સન એક વે, મતલબ આના અલગ અલગ માટે કે વેઝ હોઈ શકે, બરાબર? તો એક માટે NC કે ઇન્ટુ કે છે, બટ એવા કેટલા બધા હોઈ શકે 1 થી લઈને n સુધી. એટલે એ આપણે પ્રોબેબિલિટીઝને એડ કરી, એ છે આપણું LHS. RHS સાઇડમાં શું કરીએ છીએ કે આપણે પહેલાં ચેરપર્સનને ફિક્સ કરીએ છીએ. તો ટોટલ કેટલા મેમ્બર્સ છે? એનમાંથી એકને જ ચેરપર્સન બનવાનું છે, તો એના માટે n ચોઇસીસ છે ચેરપર્સન બનવા માટે. પછી જે વધ્યા છે મેમ્બર્સ, એ n-1 મેમ્બર્સ વધ્યા છે. હવે n-1 મેમ્બર્સ છે, એમાંથી આપણે કમિટી બનાવી છે, તો એમાં કમિટીમાં કેટલા મેમ્બર્સ છે? તો એ n-1 સેટ છે, તો એના સબસેટ્સ પાવર સેટ આપણે લઈએ તો એનું કેટલું કાઉન્ટિંગ છે? 2 raised to the power n-1. તો એ છે આપણું RHS.
Thank you. So now the same using exactly the same logic, we can prove this identity. And look at the similarity between this and the previous one. So here the summation is k multiplied by k minus 1 multiplied by nck, and that is going to be equal to n times n minus 1 times 2 to the power of n minus 2. So again, like before, you can prove this algebraically. You can prove this using differentiation, binomial theorem, and so on. But using the logic that we have just used, now you can get the same result. You don't have to go through. So instead of just, it's the same committee problem, but there is not only a chairperson, but there's also a vice chairperson. So like or a vice president or something, vice captain. So there are k choices for the captain, k minus 1 choices for the vice captain. And you see, it's the same idea. So we don't have to go through the thing again. So this way, the left-hand side, LHS, would be the number of ways of selecting the team. First select the members, then select both the chairperson, then select the vice chairperson. So that's the left-hand side. The right-hand side would be the opposite way. First select the chairperson, then select the vice captain, vice captain, and then select the remaining members. So it's the same idea. So you can keep going. Now you see, with this, once you've got the idea, you can just keep on getting more and more such identities. And maybe we don't have to spend time on this. So in fact, you get more such identities, and I won't go in that direction. But just as a by the way, if you look at the previous identity, this identity, and this identity, if you add up these two, here I've just written them down. This is the first identity. This is the second one. If you add them up, you get this identity here, which is here in green. Summation of k squared times n choose k is equal to this. But it's interesting that this is not so easy to prove using combinatorial reasoning. Notice that we proved this using combinatorial thinking. We proved this using combinatorial thinking. But this we got by adding the previous two results, which is more like algebra. So we got this using algebraic thinking. Finding a combinatorial interpretation for this is slightly more difficult. I will do that. I will leave that. All right. So can I go on, or shall we say anything? There's nothing proved out here.
Sir, you can carry forward.
Yeah. Okay. So we now look at a few summations, including one very challenging one. So let's try to find, this is a very well-known problem, find the sum of this arithmetic progression, summation of the first n numbers. So you consider the set 1, 2, 3 up to n plus 1. In what way, how many ways can we select two elements from this set? So that's the problem. So we look at the problem in two ways as usual. So the first way is, obviously it is n plus 1 C2, right? That's by definition of the C symbol. The second way is, we group the pairs according to the larger number in the pair. So it's very much like that the problem considered earlier, according to the max value. If the larger number is n plus 1, remember you have to select two elements out of the set from 1 to n plus 1. If the larger number is n plus 1, then there are n such pairs, because the other number can be anything from 1 up to n. If the larger number is n, then there are n minus 1 possibilities. If the larger number is n minus 1, then there are n minus 2 such possibilities. So keep going down like this. So you get the total number of ways is 1 plus 2 plus 3 up to n. So n corresponds to this one here. N minus 1 corresponds to this. And finally, the 1 would correspond to the situation where the larger number in the pair is just 2, because then there's only one such pair, 1, 2. So this is one way of getting the total number, and n plus 1 C2 is the other way of getting that. So therefore we get 1 plus 2 plus up to n is equal to n plus 1 C2. Okay. Of course, we have not, I have not algebraically simplified n plus 1 C2, but if you simplify it, you get the usual formula. Okay. Please let me know if I can go on.
Maybe you, can we go back and see this again?
Yeah, okay. So, so this is the, we are looking at this problem, okay? Let totally n plus 1 elements in this set.
Yes.
And I want to find the number of ways of selecting 2 elements from it. So this is a combination problem, selecting 2 elements out of. So obviously, by definition, the number of ways is n plus 1 C2. Now we are looking at the same thing. We are subdividing them according to the larger number. The larger number can be n plus 1. If the larger number is n plus 1, what about the smaller number? It can be anything from 1 up to n. So there are n possibilities. If the larger number is n, then the smaller number can be anything from 1 up to n minus 1. So there are n minus 1 possibilities. If the larger number is n minus 1, then the smaller number can be anything from 1 up to n minus 2. So there are n minus 2 possibilities, and so on. That you see the pattern.
Yes.
So this keeps going down, and finally, if the larger number is 2, then there is only one possibility. So if you add them all up, this is the total number of possibilities.
Yes.
And therefore, you get the identity.
Okay. Clear?
Okay.
Should we explain Gujarati mein? Okay.
Not
Please go
necessary.
ahead.
Oh, okay. So now in the same way, again, you can, instead of counting 2 element subsets, you can count 3 element subsets. So obviously, by definition, the number of 3 element subsets of this is n plus 1 C3, right? Now you can subdivide them according to the largest number in the 3 element subset. Suppose the largest number is n plus 1. If the largest number is n plus 1, then you have to select 2 more. Where are those 2 more coming from? They are coming from 1 up to n. So you get nc2 possibilities, right? If the largest number is n plus 1, then the remaining 2 have to come from this part, from 1 up to n. And there are nc2 possibilities. Then, so that part, now we put that aside. If the largest number is n, then the remaining 2 have to come from 1 to up to n minus 1. So you get the previous term, n minus 1 C2. So instead of, so nc2 corresponds to the largest number being n plus 1. N minus 1 C2 corresponds to the largest number being n, and so on. And finally, you can say, if the largest number is 3, then the other numbers must be 1 and 2. That corresponds to this one here. So this, if you add them all up, this must be true. 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus n choose 2 is equal to n plus 1 choose 3. Okay?
ક્લિયર આગળ જે કરું એ રીતે જ છે.
So the basic thing is just of subdividing. This is just a more complicated way of looking at this problem. Here also it's a subdivision. Here also it is a subdivision, but according to it's always looking at the largest number. So you see now, just like in the previous situation, now you can keep on getting more and more identities of this kind. So instead of looking at 3 element subsets, you can look at 4 element subsets. And you get this identity. N plus 1 choose 4 is equal to n choose 3 plus n minus 1 choose 3 plus n minus 2 choose 3 all the way up down to 3 choose 3. So it's the same thing. You subdivide the all possible 4 element subsets according to the largest number in that subset. So if the largest number is n plus 1, you get n through nc3 such subsets. If the largest number is n, you get n minus 1 C3 such, and so on. You just, so all this is just you're counting the same thing in 2 different ways. In fact, this is the standard approach in combinatorial thinking. You're counting the same thing in 2 different ways. Okay. And all these, that's why I've written summation 3. So what we considered in 1 and 2 and 3, all of them are known in combinatorics as something called the hockey stick theorem. And this is basically the theorem. This is the Pascal triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on. And look at this colored yellow. Go down from start anywhere on this end, this line out here, this edge. Go down a diagonal any number of places, add them up consecutively, and the sum will be equal to the number just below the tip. So for example, 1 plus 3 is equal to 4. 1 plus 3 plus 6 is equal to 10. 1 plus 3 plus 6 plus 10 is equal to 20. 1 plus 3 plus 6 plus 10 plus 15 is equal to 35. So in terms of the previous notation, this 1 is 2C2, 3 is 3C2, 6 is 4C2, 10 is 5C2, and 15 is 6C2. And if you add them all up, you get 7C3. So this is the same, it's the what we proved just above. And it's called hockey stick because this is the shape of a hockey stick. And that's all. It's a quite a well-known theorem. So it holds for anything. For example, 1 plus 5 is equal to 6. 1 plus 5 plus 15 is equal to 21. 1 plus 5 plus 15 plus 35, that will be 55, will be equal to the element here, which I have not shown, whatever comes below. Sorry, 56, not 55, 56. That will be 35 plus 21. So it's quite easy to prove this using induction also, but this is a combinatorial way of proving it.
ક્લિયર બધાને? જે આપણે આગળ જે થર્ડ નંબરનો જોયો હતો એનું જ અત્યારે વિઝ્યુઅલાઇઝેશન છે કે જે આપણે પેલું પાસ્કલ ટ્રાયંગલ હોય છે તો જે એડિશન છે જે આપણે 2C2 + 3C2 એટલે જે કોઈ બી લાઈન આપણે લઈએ છીએ પેલી સ્લાન્ટમાં તો એનો એડિશન છે નીચે દેખાય છે 35 જે ગ્રીન કલરમાં છે વિચ ઇઝ નથિંગ બટ 7C3. આ દેખાય છે હોકી સ્ટિક જેવું એટલે આ પ્રોબ્લેમનું નામ હોકી સ્ટિક પ્રોબ્લેમ.
Okay.
આ મેરુ પ્રસ્તારણ છે.
Yes. It's also the Meru Prastar. Yes, exactly. Yeah, so I'll move on. Now I'm going to look at something a little bit more complicated. This is a more challenging problem. Can we use combinatorial reasoning to find this sum of 1 squared plus 2 squared up to n squared? Normally the problem is just given, the formula is given, and you're asked to prove it using induction. So here we are not going to use, we are not given the formula. We are going to try to invent a counting problem and get the answer for this. So this is very, very interesting problem. So what we are going to do is, we are going to invent a suitable counting problem. And here it is. Let n be any positive integer. And I'm going to consider all possible triples of positive integers between 1 and n plus 1. ABC such that 1 less than or equal to all these 3, less than or equal to n plus 1. But with these two added conditions. C should be the largest out of ABC. So A is less than C, B is less than C. But we permit A and B to be equal. All right, so I hope the situation is quite clear. C is the largest of the three, but A and B are allowed to be equal. So let's look at two examples. If you say n is equal to if n is equal to 1, that means you want 1 less than or equal to ABC less than or equal to 2, which means C has to be equal to 2. Since C has to be strictly more than A and B, C has to be equal to 2, and therefore A and B both are equal to 1 each. All right. Now let's look at the situation when n is 2. So that means 1 less than or equal to ABC less than or equal to 3. So if the largest number is 2, then you just get that combination here, 1, 1, 2. And if the largest number is 3, then you get 1, 1, 3, 1, 2, 3, 2, 1, 3, and 2, 2, 3. There are these possibilities. So there are all these possibilities, right? So now, so that means there is only one triple in T1, and there are 5 triples in T2. So we are now going to find the cardinality of Tn in 2 different ways. That's always you find the same theme coming up in all these problems, to calculate the same thing in 2 different ways. So the first way is, let's look, this is I've just put down the definition again. Tn is the set of all triples, 1 of ABC, such that A is less than C, B is less than C. Now, since C Now, this is you look at this line very carefully. Look at each possible value of C. Once you've fixed C, each A and B can be any number from 1 up to C minus 1. Right? Because A has to be less than C, which means A can be anything from 1, 2 up to C minus 1. Similarly, B can be anything from 1, 2 up to C minus 1. So that combination A and B, since both of them can have C minus 1 possibilities, together they have C minus 1 squared such possibilities. And C can be anything from 2 up to n plus 1. So C minus 1 squared will be 1 squared, 2 squared, 3 squared, up to n squared. So that means the cardinality is the sum of the numbers, sum of the squares of the numbers from 1 to n. So first, I want to make sure that everyone is clear on this before we move on.
પેલા જે ટીએન સેટ આપણે જે માનો છે એ તમને સમજાઈ ગયો ને. ટીએન સેટ છે એ ટ્રિપ્લેટ્સનો સેટ છે એબીસી વિથ કન્ડિશન. કન્ડિશન શું છે કે એબીસી છે એની ક્યાંથી ક્યાં નેચરલ નંબર્સ ફ્રોમ 1 થી લઈને n+1 સુધી છે, જેમાં સી એક પર્ટિક્યુલર છે કે સી ઇઝ લાર્જેસ્ટ અમંગ એ એન્ડ બી. એટલે સી એથી પણ મોટો હોવો જોઈએ, બીથી પણ મોટો હોવો જોઈએ. બટ એ અને બી ઉપર આપણે કોઈ રેસ્ટ્રિક્શન નથી લેતા. એ બીની બરાબર બી હોઈ શકે અને એ બીથી અલગ બી હોઈ શકે છે. તો સી માટે કઈ કઈ કન્ડિશન્સ હોઈ શકે? સી 1 તો નહીં હોઈ શકે, કારણ કે આપણે જોઈએ છે એ અને બી લેસ ધેન સી છે હોવા જોઈએ. સો સી વિલ બી, સી માટે આપણે કયા કયા એઝમ્પશન્સ થઈ શકે? સી કાં તો 2 હોઈ શકે, કાં 3 અપ ટુ n+1 સુધી આપણે લઈ શકીએ છીએ સીને. એવી રીતે એ અને બી છે, સી ચૂઝ થઈ જાય પછી એ અને બીને આપણે કન્ડિશન છે એ લેસ દેન સી, બી લેસ દેન સી. તો આપણે એ અને બીને ચૂઝ કરવા માટે C-1, એને ચૂઝ કરવા માટે C-1 પોસિબિલિટી છે. એવી રીતે બીને બી C-1, કારણ કે A = B બી હોઈ શકે છે. તો ટોટલ એ અને બીને ચૂઝ કરવા માટે C-1 સ્ક્વેર પોસિબિલિટીઝ છે. હવે સી આપણે ખબર છે સી ક્યાંથી રેન્જ થાય છે 2 ટુ અપ ટુ n+1. હવે સીની વેલ્યુ આપણે આમાં નાખશું તો 2 - 1 1 સ્ક્વેર, 3 - 1 2 સ્ક્વેર. એ આખે આખું સેટ TN બની જશે. રાઈટ?
Okay. So now so this is the first way of calculating. Now let's look at what the other way is. So as usual, we are going to subdivide the triples into two categories. One kind is in which the numbers are all different. C is of course different from A and B, but it could happen that A and B are also different, or it could happen that A and B are the same. So the first category is one in which all three are different. A, B, C are different. And the other category is one in which A and B are the same. So that means the triple is of the type AAC. So there are two types. So let's count both. Let's count both these triples. So if you have all three are distinct, if A, B, C are distinct, then the number of possibilities is basically you're choosing any three numbers from the first n+1 numbers, right? Because all these numbers are from the set 1 up to n+1. So you have to choose any three, but A and B can be flipped. It's either the smaller number first and then the bigger number, or the other way around. Because between A and B, there is no order relation. So n+1 choose 3 and then multiplied by 2 because A and B can be flipped. So this is the number of possible triples in which A, B, C are distinct. That means unequal. Now let's look at the other situation where these two are the same. If these two are the same, that means really you're only selecting two numbers, because the third number is the same as that A. So you have to select only two numbers from the set 1, 2 up to n+1. So it is this. I hope that is all right. If all three are distinct, then you will get this number. If these two are the same, then you get this number. Once you accept that, immediately you get this identity. 1 squared plus 2 squared up to n squared is equal to 2 times n+1 choose 3 plus n+1 choose 2. So tell me which part we should go over again.
Sir, maybe first part.
This part, this one?
2 times n plus 1 C3.
Yeah. Yeah. So, I mean, you want me to repeat or you will repeat? So I'll repeat first. So, sorry. So let's look at this line. Now, there are two types of triples. One in which the three numbers are all different. A, B, C are all different. If they're all different, that means ABC is basically a subset, a three-element subset of 1, 2 up to n plus 1. And the number of subsets is n plus 1 C3. But we have to multiply by 2 because AB can be the smaller number first, then the bigger number, or the bigger number first and then the smaller number. It can, because both are allowed. So therefore 2 times that. And if you have first two elements repeated, if they are thus equal, then A and C are just make up a 2-element subset of 1, 2 up to n plus 1. And number of 2-element subsets is just this, n plus 1 C2. So if you add up this and this, it should be same as the other way of counting the number of triples, which is 1 squared up to n squared. Okay.
જે ફર્સ્ટ પાર્ટ શું કહે છે? ઓકે, એ બી એક મેક્સિમમ તો આપણે ગોતી શકીએ છીએ, રાઈટ? તો હવે એ બી ને તો આપણે ઇન્ટરચેન્જ કરી શકીએ, એ આગળ બી પાછળ. તો એ ઉસકી દો પ્રોબેબિલિટી ના, હા, એની બે પ્રોબેબિલિટી આપણે ડિફાઇન કરી છે. આઈ એમ સોરી.
ઓકે,
બીજો પાર્ટ તો આપણે ઈઝી છે. એ સી છે, તો કોઈ પણ બે જ એલિમેન્ટને ચૂઝ કરવાનો છે, n પ્લસ 1 C2.
Okay. So now you'll find this final formula. I'm going to twist it a bit. Look at this formula. N plus 1 choose 3 plus n plus 1 choose 2 is equal to n plus 2 choose 3. That is that formula which we had proved. It's, that's the Pascal triangle formula, right? Each element is the sum of the ones immediately above it. N plus 1 choose 3 plus n plus 1 choose 2 is equal. So if you combine it with this, here there are 2 of these and 1 of these. If you take just 1 of these and 1 of these, together they will give you this term here. So this is a nicer way of putting that formula. The sum from 1 squared up to n squared is equal to n plus 2 choose 3 added to n plus 1 choose 3. So that's a nice result, quite different from the usual result. All right. And if you algebraically simplify this, you get the usual answer. So I've shown that on the next page. Here it is. If you algebraically do n plus 2 choose 3 plus n choose 3 is this, and n plus 1 choose 3 is this. Take out n times n plus 1 upon 6 common, and you get n plus 2 plus n minus 1, which simplifies to 2n plus 1. So it just simplifies to the usual formula. N times n plus 1 times 2n plus 1 upon 6. But this is algebra. This part is just shown. I'm showing you that the same answer comes out in the end. All right, so shall we move on?
Yes, sir.
Okay, one quick, again from the binomial theorem, you have this result. And in this result, if you put x equal to -1, -1, then you get n choose 0 minus n choose 1, n choose 0 minus n choose 1 plus n choose 2 and so on, plus -1 to the power of n, n choose n, is equal to 0 to the power of n, which means 0. Now, what that means is, if you take all the positive terms on one side and negative terms on the other, basically the statement is n choose 0, nc0 plus nc2 plus nc4 and so on, is equal to nc1 plus nc3 plus nc5 and so on. Now this here is the total number of subsets with even number of elements, even cardinality. And this here is the total number of subsets with odd cardinality. So basically this statement is saying that the number of even subsets is equal to number of odd subsets. Now, but notice that proving it, we use algebra, we use the binomial theorem. So is there a way of establishing that the number of even subsets is equal to the number of odd subsets just using combinatorials? So I'm going to show you such a proof. So in this set S, let X be any fixed element. So one element is taken some fixed one, and using that one element, I'm going to divide the subsets into various categories, a two-way classification. So it's like this. Either the cardinality could be odd, cardinality could be even. That's one way of subdividing. Or the subset contains X or doesn't contain X. So I hope this classification that is put down here is clear. Either the subset, any subset either has odd cardinality or even cardinality, and either it contains X or doesn't contain X. So these sets here, A is all subsets which contain X and have odd cardinality. B is all subsets which contain X but have even cardinality. C is all subsets which don't contain X and have odd cardinality. D is all subsets which don't contain X but have even cardinality. Now I'm going to establish a bijection. Just watch. Suppose T, take any subset of this kind. That means it has odd cardinality and it contains X. Well, since it contains X, I can take out X from it. I can remove X from it. Once I remove X, what happens to that new set? Well, since it goes from this category to this category, right? Because the T contained X, by removing X, it becomes not containing X. And T had odd cardinality. By removing one element, it becomes even cardinality, which means that by doing this operation, you're ending up with a subset in this category, right? By starting with a subset here and removing that X, I end up with a subset here. And the reverse is also true. If I start with a subset here, by just adding X to that subset, I end up with the subset here. Now, this is obviously a bijection, right? It's a bijection between A and D. That means what it shows is that there are as many subsets here as there are subsets here. You can establish a one-to-one connection, one-to-one mapping between subsets which have odd cardinality and contain X, and subsets which have even cardinality and don't contain X. There's a one-to-one mapping between them. So that means this cardinality is equal to this cardinality. And in the same way, this cardinality is equal to this cardinality. Because if it has even cardinality and contains X, I can remove X and I will get a subset of this kind, which has odd cardinality and doesn't contain X. So so that means you have A and D equal in cardinality, B and C equal in cardinality, which means that A union C is equal to B union D in cardinality. And A union C means all those which have odd cardinality. B union D means all those which have even cardinality. So I've got established this, that odd is equal to even. So this is notice we have proved this combinatorially and not algebraically. Okay.
સમજાઈ ગયું બધાને? આ કઈ રીતે આવ્યું છે કે એક વખત રિપીટ કરું? ડન? સર, you can move forward.
Okay. All right. Now I'm going to talk about one very famous connection which comes from ancient Indian mathematics, which shows that in ancient India itself, they had hit upon the Fibonacci numbers, and therefore the correct name for it is not Fibonacci numbers at all. But they stumbled onto the Fibonacci numbers in quite a different way from the person called Fibonacci. So usually the Fibonacci numbers are defined via an arithmetic property. That means you have 0 plus 1 is equal to 1, 1 plus 2 is equal to 3, and so on. Each pair gives the next number. But it turns out that the Fibonacci numbers can also be defined combinatorially. And that makes it a very interesting thing. What combinatorial interpretation can there be in it? And it so happened in ancient India. I think you may have actually seen this. It's quite well known. But I'm going to connect it with another problem, which is called about compositions. So this is like a prelude to that. A composition of n is basically an expression for n as a sum of positive integers, but it's an ordered sum, which means that the individual portions can be shuffled amongst themselves, permuted. For example, these are the compositions of 3. You can write 3 as 3 itself, or 2 plus 1, or 1 plus 2, or 1 plus 1 plus 1. So there are 4 compositions for 3. So suppose I write an for the number of compositions of n. So that means A3 is equal to 4 because we've got these 4. So basically the question we are going to ask is, find a formula for this number. And it turns out an amazingly simple formula is going to come out in the end. All right. So this is not going to give you the Fibonacci numbers. That comes out in a related problem. That will come out next. So let's see. So this table, in fact, it has all been computed in one go. But let's see. Let's look at the very first row. Compositions of 1. Well, there's only one possible composition of 1, right? As 1 itself. So A1 is 1. Sorry. What happened? So there's one composition of 1. Now let's look at 2. What are the compositions of 2? Either you have 2 itself, or you have 1 plus 1, which means the total number is possibilities is 2. Now let's look at 3. We just looked at 3 a moment back. So it's 3, 2 plus 1, 1 plus 2, and 1 plus 1. So there are 4 possibilities. Now let's look at 4. Either you have 4, or you have 3 plus 1, 1 plus 3, then 2 plus 2, then 2 plus 1 plus 1, 1 plus 2 plus 1, 1 plus 1 plus 2, and then 1 plus 1 plus 1 plus 1. So if you count these, you get 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possibilities. And if you take the trouble to do it for 5, and I have listed out all the possibilities here, you'll notice all like 4 plus 1, 1 plus 4, 3 plus 2, 2 plus 3, 3, 1, 1, 1, 3, 1, 1, 1, 3, and so on. You end up getting 16 possibilities. And this pattern, 1, 2, 4, 8, 16, is so unmistakable. So it seems as if we have got a beautiful result out here, that A subscript n is exactly equal to 2 to the power of n minus 1. So A3 is equal to 4, A4, which is 2 cubed, A5 is equal to 16, which is 2 to the power of 4, and so on. So this seems to be the conjecture. This is what our experiment has suggested. So how are we going to prove it? Now, one way of proving it is this. Now, this is where you'll have to look very carefully at the logic that we're going to use here. Look at, there is only one composition of n in which there is just one summoned. That means only one part in the sum. That is by n itself. So if you look at these here, for example, 5 is this is the only composition which has only one summoned. This is the only composition of 4 which has only one summoned, and so on. So there is just one composition of n having one summoned. Now we consider all the compositions which have more than one term. Let that first term, call that first term k. That means what have we got here? The first number is k. K can be any number from 1 up to n minus 1. It cannot be n itself, because then there would be only one term in that composition. So it's only 1. So that means the composition is of this kind. It is k plus something else. All right. I hope this is clear. So the k is the first term, and then a number of other terms are there, which obviously must be adding up to n minus k. K to get n. Right? Now, these terms can be permuted any way you want. And each permutation that you get out here, if you can shuffle these numbers here, will give you a different composition of n minus k, and all of them can be combined with this k to give you a particular composition for n. All right. So that means, now just look at what we have found. That means among all the compositions of n, if you just block the first term to be k, then the remaining terms form a composition of n minus k, and you can give all possibilities in that remaining part. So if you combine these two, you end up getting this result out here. This is the important result. So a subscript n is equal to 1 plus a1 plus a2 plus up to an minus 1. Now let's understand each of this thing fully. An minus 1 corresponds to the first term being 1, and the remaining terms adding up to n minus 1, but they can be shuffled among themselves in an minus 1 ways. This corresponds to the first term being 2, and the remaining terms can be then shuffled, which add up to n minus 2, can be shuffled in n minus 2 ways. Then the previous term is the one in which the first term is 3, and the remaining terms can be shuffled and they add up to n minus 3 and so on. And this one corresponds to the very first term being n minus 1. And well, there is only one term left over, so it's like 1. Sorry, I said that wrong. This term corresponds to that. And this one corresponds to that original one where there is only one summoned, in which n is the sole summoned of the thing, sole term in it. So this part needs to be understood carefully. Perhaps if you can, if it needs explanation. So it comes from this basically.
तो हम लोगों को क्या कंप्यूट करना था? वी वर जस्ट ट्राइंग टू डीकम्पोज, मतलब हम एन को ब्रेक कर रहे हैं अलग छोटे छोटे पार्ट्स में. तो हमने शुरू किया, एन को हम कैसे लिख सकते हैं? एन की तरह लिख सकते हैं, ठीक है, एक तो वही हो गया. फिर इसके बाद एन माइनस 1 प्लस 1, ठीक है. 1 को ज़्यादा आप नहीं कर सकते, पर अगर हम के ले तो के के बाद जो प्लस होगा, उसके बाद जो एन माइनस के बचेगा, उसको आप फिर से ब्रेक कर सकते हो. पर वो ब्रेकिंग किसकी, मतलब वो जो हमने तोड़ तोड़ के छोटे पार्ट्स में लिखा, वो एन माइनस के का कॉम्पोजिशन हो गया, है ना. तो एन इज इक्वल्स टू के प्लस कॉम्पोजिशन ऑफ एन माइनस के, ठीक है. अब हम अगली स्लाइड पे जाते हैं. तो अब देखिए, अब ये फुल फॉर्मूला हमने लिखा. ए एन टर्म क्या डिनोट करता है? कितने एन के कॉम्पोजिशन हम लिख सकते हैं, ठीक है. तो अब इसको उल्टा देखना शुरू करते हैं, ए एन माइनस 1 से, है ना. अगर ए एन माइनस 1 है तो पहला टर्म अगर हमने के को 1 ले लिया तो बाकी क्या बचा? एन माइनस 1. तो ए एन माइनस 1 सारे कॉम्पोजिशन बताएगा, ठीक है. फिर अगला 2, तो फिर 2 के को 2 लिया तो एन माइनस 2 के कॉम्पोजिशन बचे, तो वो ए एन माइनस 2. फिर ऐसे करते करते ए 1 पे आ गए, जिसमें के की वैल्यू क्या है? एन माइनस 1. तो ए की बचा अपना कॉम्पोजिशन ऑफ 1. और लास्ट टर्म n 1 है. क्यों? क्योंकि उसमें हमने n को n ही रखा बस, ठीक है.
That's right. Okay, now this is like an identity. That means this function a of n which we are trying to get is the sum of all the a values before it with 1 added to it. Now if it's an identity, it will hold for all values of n. So we replace in this a n by n minus 1. So what do we get? A of n minus 1 is equal to 1 plus all the numbers before it. So it's equal to 1 plus a1 plus a2 up to an minus 2. So that means here, this part here which we have got is just this part here. So that means a of n is equal to, this part is same as a of n minus 1. And we've already got a of n minus 1. So it's just a of n is equal to a of n minus 1 plus a of n minus 1, which means a of n is equal to 2 times a of n minus 1. So that means this is a doubling sequence. And that's it, we have proved it. And since a1 is equal to 2 to the power of 0, it follows that n is equal to 2 to the power of n minus 1. So I think this part we may not need so much explanation. The main thing is really understanding why this is true. If this is true, by substitution, you get this. And I mean, by replacing n by n minus 1, you get this. And then it's just some algebra after that.
ये ठीक है ना, कुछ किया नहीं हमने ज़्यादा उसमें, an-1 था और an-1 हमने ऑब्जर्व किया कि क्या है, और फिर बस वो वहाँ पे रिप्लेस कर दिया हमने 1 से an-2 को an-1 ही कर दिया, ठीक है बस. So 2 an-1. Okay.
Now you might wonder, you might ask, is the above what we have just shown, is it a combinatorial proof at all? Because there was a lot of algebra in it, right? Well, the answer is it is not. It is not fully. There is a crucial combinatorial part of it, which is that recursive thinking. You know, if you've done some computer programming, you'll know what recursive thinking is. That is, from n, we made use of something which is true for a smaller one. That's how that a of n minus k came into the picture. So that recursive part is crucial. So is there a purely combinatorial proof? There is, but I don't, since we may be running short of time, I won't, sorry. So I'll just quickly go over it. There is a purely combinatorial proof. And that is, suppose you're given n is more than 1, and you're given n objects in a row, they define n minus 1 spaces. For example, if there are 2 objects, so I'm using these bullet points for the objects, and the spaces, I'm using this symbol here, a heavy underscore. So if there are 2 objects, there is 1 space. If there are 3 objects, there are 2 spaces here. 4 objects, there are 3 spaces here, right? So that's quite clear. Now, the crucial thing is that any subset of these spaces defines a unique composition of n. For example, suppose you take n equal to 4. We are showing the subsets using a red diamond. So for example, there are 4 bullets here, 1, 2, 3, 4. So that means 3 spaces. Out of those 3, I have selected these 2, which I've shown with a red color, and I have not selected this one. So this selection corresponds to so 2 bullets and then another 2 bullets. So sorry, just I take that back. The red ones, the red color sort of demarcates. So it is 1 plus 2 plus 1. So 1 to the left of this red diamond, then 2 in between these 2 red diamonds, and then 1 more here. So 1 plus 2 plus 1. Similarly, this one, so out of the 3 spaces, I select only that middle red diamond. So this is 2, and this is also 2. So it corresponds to 2 plus 2. And if it's this one, it is 3 plus 1. So you see, so there is an exact 1-to-1 correspondence between the subsets and the number of and the compositions of n. So you get, so this is an old problem, the number of subsets. So you'll notice this is a very short, very elegant proof, which is different from what I just showed you. And you might say, why didn't we just look at this right away? Because this is a purely combinatorial proof. It is much more elegant and it is shorter than the first proof, which was based on some recursive thinking, plus some algebra. Well, the reason for that is it is related to our next example. And this is an important historical fact, I think, which people who study ancient Indian mathematics have found that there was a great interest in recursive thinking in ancient India. And you will find it coming out in this very problem, in the next problem that we're going to look at, and in multiple other ways, which we perhaps, not just in combinatorics, but also in algebra. So let's look at this. Just a minute, before I go on, how are we doing on time? How much?
So we would kind of like to finish maybe in 5 more minutes.
Okay, so then this will have to go very fast. Unfortunately, I was also going to do something on pan-diagonal magic squares, but obviously there is no time for that.
Maybe we should have another session from you.
So this one is quite well known. So I'll go a little bit faster out here. So this is, in fact, the origins of this problem go all the way back to B.C. It has been studied by Pingala, who is a grammarian, and by some of our famous mathematicians, Virahanka, Gopala, Hemachandra, all quite a long time back, 12th century and so on. So what is the problem? You're looking at syllables and dividing the syllables into two kinds, depending on the length. A syllable comes to, it's either a beat or 2 beats in terms of the length of the syllable. So we just categorize them as short, whose length is 1 beat, or long, whose length is 2 beats. So this is just for simplification. It may not actually come out exactly like that in practice. So you can think of them as S and L. Now, you can form words using S and L, and we categorize them according to their total length. So if total length is 1 beat, then there's only one word possible, S. If you want a word of length 2 beats, you can have SS, right, 1 plus 1, or a single L, which has length 2 beats. So both ways you get a word which is 2 beats long. So just like before, you can ask for this for the solution of this problem. Find the number of words with length n beats. So let's that number be Cn. So we just found out that C1 is 1 and C2 is 2. So let's look at C3. C3 means the word should have a length of 3 beats. So one possibility is SSS. Another possibility is SL. That means 1 plus 2. Another possibility is LS. That is 2 plus 1. So all of them have length of 3, and there are 3 possibilities. If you want a length of 4, you can have SSSS, 1 plus 1 plus 1 plus 1. SSL, which is 1 plus 1 plus 2. SLS, which is 1 plus 2 plus 1. LSS, 2 plus 1 plus 1, or LL. So there are 5 possibilities. And you keep going like this, and you find this number sequence being generated in the last column is 1, 2, 3, 5, 8, 13. Well, that's the very famous sequence. So these are these values which you get. And we observe that the C's are just a displaced Fibonacci sequence. And now we need not spend too much time on the proof, because the idea is exactly the same. So you consider all words with n beats, and each word ends either with a short with S or with L. Remove that last syllable entirely. So what happens if the deleted letter is S? Then the reduced word, the modified word, must have length n minus 1, because you've removed 1 beat basically. If the deleted letter is L, the modified letter must be having length n minus 2. So for example, look at the case of n is equal to 5. I've listed out here all the words whose length is 5. For example, LLS means 2 plus 2 plus 1. Then LSSS means 2 plus 1 plus 1 plus 1. All these have length 5. The red color ends with S. So all of them end with the S. All these end with L. If I remove the S, then I get LL, LSS, SLLs, SSL, and so on. These are basically all the words whose length is 4. And these are all the words whose length is 3. LS, SL, right? So if you delete the last syllable, this is what you get. All words with length 4, all words with value 3. So that means C5 is equal to C4 plus C3. So basically you get the number of possibilities with n is equal to the sum of the previous 2, which means it follows the Fibonacci recurrence. And since it agrees right at the start, the initial 2 numbers are 1 and 2, which means the initial 2 numbers are a pair of consecutive Fibonacci numbers. So therefore, every number is a Fibonacci number by inductive reasoning. And of course, now that means the more correct name would be this. So we begin to see from here that these numbers have an unexpected combinatorial meaning, which arithmetically does not come out. And there are many variations on this theme which are possible, which I won't go into them right now. So I was also going to go into this question, which is not possible now. I was also going to go into this question, which I'll just, which it just takes a moment because I'm not going into. So you're looking at a situation where you're trying to stack these shapes, which are called dominoes, and making a bigger rectangle out of them. So you can put this horizontally or you can put it vertically. So how many ways can you do this? And if you do it, I've shown it using a red color indicating a vertical domino, a green color. So for example, these are all the ways of getting a 2x5 rectangle. 5 vertical or 2 vertical and 2 horizontal, 1 vertical, 2 horizontal. And so it's quite easy to show that this is also a Fibonacci number. Okay. So I'm just going to end with my last part here. So in terms of looking at topics connected with our ancient past, there's only one situation that we looked at in detail here. There are many such situations which we could have. And I'm going to only quote some poetry here. What is the significance of connecting this? To me, this is the significance. I'm quoting a famous piece of poetry out here. So it does not need any meaning. A thing of beauty is a joy forever. So that brings me to the end of the talk, and I hope we have been able to experience this beauty together. Thank you.
Thank you so much, Professor Shailesh.
Thank you. Thank you, all of you.
I just want to make a quick remark that the last thing that we were discover ये जो अभी आखिरी में हम देख रहे थे फिबोनाची वाला सीक्वेंस, उसमें हम वो लेंथ ऑफ लेटर्स देख रहे थे, वो हमने अपने लास्ट सीसीएल सेशन में भी करे थे. आपको याद होगा धा दिन दिन दा कि वो वही था. और आपके पास कोई सवाल हो तो पूछ सकते हैं.